Alright guys, here's one of my all-time favorite problems here, okay? Making a three-dimensional box, a box without a lid, by cutting out the corners of this sheet of cardboard or whatever your material is, okay? So what we do is this. We cut out the corners, as you can see, cut out equal corners, whatever the dimensions are, we don't know yet. And then we fold it up, and when we fold it up, we see what happens, okay? The length previously, which was A, is now diminished by 2x because you chopped off x from each side. The length B is diminished by an x and another x, so now the width of our box is B minus 2x. Okay, and then the height of our box is designated as x. So again, okay, we can vary this dimensions of this box, okay, by the size of the cut. So again, the cut is x by x out of each corner, which means that the original um, length, whatever it was, A, is now A minus 2x. The original width, which was B, is now B minus 2x because you cut off x from each side, from here and here, okay? And the height is x. Now, the objective with this problem is to find the dimensions of the box, which are which would create the largest volume. The dimensions of the box with the largest volume. Okay, so here's what we're looking at. All right, I think we believe we start with the box being a sheet of paper here, which is 6 by 8. 6 by 8. So B is 6 and A is 8, and then we make these cuts. And okay, depending on the cut that we make, we get volumes of varying quantity. So here you're watching what the volume looks like, okay, right down here at the bottom. And what we want is we want to see where that volume is maximized. So the volume is on increase here, and it's still increasing, okay, but now it's somewhere it's decreasing. All right, so somewhere in around there it's going to decrease. So what we want to do is we want to find a function which illustrates this. And so there's the box, and there's the cut. Is 1.13 is the size cut. Now, like I said, this is going to be a function, and it's not going to be a quadratic function, not at all. In fact, it's going to be a cubic function, and we'll illustrate that for you in just a minute. Okay, but the graph, okay, is going to look like this, and what we want is we want the peak, the high point on that graph. Okay, now that's going to require us to go to the calculator because it's not going to be quadratic. So we will uh, pick up with that next, and then also lend our attention to the calculator. Okay, we're back here. We're going to look at this schematic here now. Okay, so the volume of any three-dimensional box is length times width times height, right? The simple rectangular solid. Now, what do we call the length? What do we call the width? And what do we call the height? Well, we said that the dimensions of this box, okay, were well, the uncut box was x, but then we cut out x from each of the corners. So the new length is 8 minus 2x, okay? So that's the new length of the box. So we can now write a function because we need a function in order to optimize. So we're going to write a function of the volume as it relates to x. So the length was designated as 8 minus 2x, okay? The height is going to be x. The width is going to be, as you can see from the same rationale, the original length was 6, so we chopped off x from here and x from here, so this is now 6 minus 2x, okay? 6 minus 2x, and then the height is x. Now there's a function in terms of x, okay? Um, and that function is going to be cubic. You'll see by multiplying that out. Okay, we don't even need to multiply that out. But if you did multiply it out, you'd see that it was cubic. Okay. Well, I know some of you are going to want to multiply that out, so I multiplied it out nonetheless. Okay, so here it is. Okay, what I did to make the multiplication a little easier was I pulled out a negative, which allowed me to rearrange my terms here. Okay, likewise, I pulled out a negative from these guys, rearranged my terms. Okay, then the negative times the negative is a positive, so they will effectively just disappear those signs. So now I just have the product of these two binomials, which is going to be, easy multiplication, 4x squared, okay, minus 12x minus 16 and minus 28x plus 48. And then I distribute that x. So there's my cubic expression. And as I'm going to tell you, you don't really even need that. Now, don't try to optimize that without your calculator because it's not quadratic. So the only way we can optimize that is by analytically with calculus. So we have to defer that till next year, but we can look at the calculator, and we will, and I will expect you to be able to work the calculator. But before we look at that on the calculator, I want to know what range of values I need to be looking at for x. What is the optimal, what is the value of x, which makes sense, okay? Let's go back to the picture, okay? What can x vary from? What is the domain of this function? X cannot be more than 3 units, right? X can't be more than 3 because then you cut off and you have nothing to fold up, okay? So X is going to be less than uh, half the shortest side. As you can see, X is going to be less than the half of the shortest side. So the range of values for X is going to be from 0 to 3. So I'm going to go to my calculator, okay? I'm going to go back to my function. I'm going to key that function in, okay? And on my calculator, pulling up my calculator, okay? I'm going to key that function in, and again, I can just go right here to y equals, key that function in, and I've got another one in there. I'm going to turn that off. Okay, so you could either go, I could put this function in as it is, or I can write out the expanded version. Should make no difference. Since I have the expanded version, I might as well key that in. So we're going to key in 4x cubed, okay, 4x cubed minus 28x to the second power, and I can check that out, x to the second power, and plus 48x. And okay, so before I go and graph that, I want to look and see where my volume is, okay, between the range between 0 and 3. So I'm going to go to my table set. I'm going to look at 0, and let's go increments of a half, just so I can see where this thing is going to peak out, okay? So now we look at our table, and we see that the peak out value is going to occur somewhere around 24. So the y value there maxed out is about 24. So when I set my table, I'm going to go from 0 to 3 on x. That's all the more I need to go to. My y values, let's go up to about 30, so I have a little breathing room. I can see things. Okay, so now I'm looking at the graph of my function within that designated window, and I'm going to try to find out where that peak value is. Okay, so that's a F5 maximum, F5 max. All right, enter that. Scroll to the left of that peak point that we're after. All right, just a little bit to the left of it, enter. And scroll over to the right of that peak point, enter. And it's going to lock on that value of, okay, 1.13. So x is equal to 1.13. All right, so once I have x, x is equal to 1.13, x is 1.13, then that's my height. My length is going to be 8 minus twice that value of x, so just a matter of computing that. And my width is going to equal 6 minus twice that value, 1.13. And if I'm not mistaken, going back, when we were asking this to be optimized, okay, we're trying to find that high point. In fact, we'll lock it right on there. There it is, 1.13. And there's the other dimensions, 8 minus 2 times that, 1.13, 5.7, and 6 minus 2 times that. So the box, the dimensions of the box of greatest volume are a height of 1.13, which we found by going to finding our function, how to find our function, and it being quadratic, we had to go to the calculator, okay? And on the calculator, okay, where's the calculator? On the calculator, we graph that function, okay? Our rationale told us that the maximum size of that cut would have been 3, would have been 3 units, all right? So within our calculator, we're only looking for those values of x between 0 and 3. So we did our table set, and then we looked at our table between 0 and 3 to see where that was maximizing out. Then we did our window set. So the x ran from 0 to 3, and then the y's ran up to what looked like the maximum, about 24, but give ourselves some breathing room. Okay. Then we graphed the function. Okay. And looks pretty much like what we see over here. Okay, we're trying to find that high point. So that's F5. And we're going to max. And so max then says, let's go first to the left of that point of interest. Enter. Then scroll over to the right of that point of interest. Enter. It locks on. Tell you exactly what that high point is, the value of x. So it maximizes out with a volume of 24.25 when the size of the cut, x, is 1.13. That being the x, which we designated as the height, the width being 8 minus 2x, and the length being 6 minus 2x, gave us the dimension of the box with the optimal volume. There you have it.